Hi, everyone, and welcome to a new episode of the show. Today we have Pavel Hrmo with us, who's going to be talking about trapped ion quantum computers. We're going to tailor this discussion around potential enhancements that can be made to the field going forward and how we can make these systems better, more accurate, and more scalable. I hope you enjoyed the discussion, and let's jump into it. Hey, Pavel, thanks a lot for joining.
Thanks for having me here, Nicholas. I'm very happy to join your channel.
Cool. Today we're going to be talking about trapped ion quantum computers, which is your specialty. Maybe before we get started with the actual quantum computers, maybe you can talk briefly about the research you're doing now and sort of how you ended up where you are.
Right, so what I'm currently working on is, as I said, trapped ion quantum computing, but more generally, I am an atomic physicist, so I have a PhD that focuses on working with atomic systems, and kind of my passion, or what reason I got into this field, is because I found a lot of phenomena that you can observe in atomic physics and quantum physics really fascinating. So throwing out buzzwords like quantum entanglement, interference, superposition, these are all things that really interested me as I was learning a bit more of an undergrad. And then I naturally sort of gravitated toward this field. And when I started learning about trapped ions, I learned that these systems actually are not just cool in of themselves, but actually have some really potential applications as quantum computers. And so then after my PhD, I joined a world-leading group in the University of Innsbruck, which has a record of pioneering quantum computing in trapped ions. And I spent 3 years there as a postdoc, and then I moved to ETH Zurich to continue pursuing this in a slightly different platform, and essentially harnessing what I learned both at the PhD level and at the postdoc level to bring together a new platform for trapped ion computing, and one that we believe here at ETH is going to be more scalable and is going to compete with some of the leading players in this quantum computing sphere.
Mm. Is it fair to say that you then ended up with specifically trapped ion systems because you have a sort of atomic physics background? Because you have a number of different architectures, right? And trapped ions are not necessarily the most common of them. Is the reason for you ending up in that space that you had sort of the natural background to go into it, or is there another reason why you picked trapped ion quantum computers in particular?
I would say that at the time when I was kind of choosing what topic to go into, there was a lot of interesting physics if you look at it from the perspective of just atomic physics. For example, neutral atoms were very in vogue as well. Things like Bose-Einstein condensation research seemed very interesting on a fundamental level. But it was not necessarily obvious how to directly harness this into maybe turn into a technology and make something useful with it. Nowadays, we're seeing a lot of progress with neutral atoms, for example, when they can be trapped in optical tweezers. Now, these platforms are very successful with researchers in France, in the US, for example, at Harvard. And there's also spin-off companies using this technology. So I think now the field has matured and has improved very quickly, where a lot of the neutral atom things also became much more technologically advanced. But I would say when I was starting, like 7 or 8 years ago, trapped ions were, let's say, the ones that had demonstrated the earliest, let's say, building blocks of a quantum computer. They're one of the first systems that could perform entangling gates and really do them deterministically. Like, for example, you could do entanglement with photons, but it used to be a very probabilistic process, and it wasn't really obvious how this would, scale to large systems. And people thought, well, with ions, it's not easy, but let's say there is a clear pathway. So at that moment, I thought of all the different platforms, ions were nice because they were something, that I could really see and grasp. And basically, I had the opportunity to work in a research lab that was in London at the time, and I really enjoyed, starting in my path with these sort of platforms. Yeah.
Mm-hmm. And looking forward, or stepping forward now to the current point in time, we have quite a lot of architectures in the market, and they're also a bit more mature, perhaps, than when you embarked in the space.
Yeah.
Is your view that trapped ion quantum computers currently and in the future are very relevant as a competing architecture, or do you feel like they sort of lost a bit of that, prominence maybe in the hierarchy of architectures?
So I would guess address this in two ways. One is sort of like, let's say, the finance manager look at it, and then the other is more the scientific way. So I would say in terms of money that has been spent indirect investments in sort of quantum computing. I mean, I might get this figure slightly wrong, but I believe trapped ions still represent almost 25% of all the investment into quantum computing. So I would say that there's still a very significant portion of the industry at the moment. And we also have some startups, for example, like IonQ, that went public and have been able to raise massive amounts of money off the back of their successes. So I would say that they didn't necessarily lose relevance. I think they are still very relevant when you look at it as a big chunk of the pie of money that's being spent on quantum computing. Now, on the second, let's say more technical or scientific question, and this is maybe where you're coming from, is that maybe what's been more in the media and what's been seen more are the recent successes in the superconducting qubit architectures, where, for example, companies like Google and IBM have really pushed, let's say, the state of the art to, let's say, qubit numbers in the high tens to hundreds. And there were these demonstrations, for example, of the first, let's say, quantum advantage, or the first results that were not classically simulable by a computer. And in this sense, I believe that they have, let's say, demonstrated a bit more than trapped ions, but I would view this as somehow more of a short-term success. None of these systems has really shown that they can really take what they have now and go from 100 to 10,000 to 100,000. So I still view the playing field as very open, and latecomer technologies might catch up very quickly. And this example of the neutral atoms I brought up is actually very relevant, because the tweezer technology has improved so rapidly, and their gate fidelity so rapidly that they're going to be very relevant in the next few years, I believe, and they'll be competing with the trapped ions with the superconducting qubits. So even these latecomer technologies can get in the game, and ultimately the key word I want to focus on in this interview is going to be scalability, because I think in the near term a lot of demonstrations, cool things can be done with these maybe 50, 60 qubit systems or 100 qubit systems, but to really build a large, scalable, and fault-tolerant quantum computer, it will require error correction. And to have error correction, you will massively need to increase the number of qubits that you use to encode the information. And so I don't think there's a clear winner, and I wouldn't even say that superconducting qubits are like leading the way. Certainly they've had the most publicity. There's certainly a lot of great expertise and I would say well-established teams, because they're run in big corporations like IBM and Google. But I think a lot of the startups are attracting really bright quantum physicists from all around the world, and that's why there is a dynamic where some breakthroughs can maybe accelerate you much quicker on the path to scalability. And this is where I see trapped ions now as well, that we hope to have some really cool ideas soon that will enable this.
Mm-hmm. Great. So I think as a segue to the scalability topic, maybe we can just briefly talk about the pros and cons of trapped ions or trapped ion quantum computers right now compared to some of the other architectures out there. Sure. This could potentially change rapidly, but at least as as it looks right now, could you maybe summarize the key pros and cons of trapped ion computers compared to the other architectures?
So I would say one of the first cons really comes from the physics of everything, and that's the fact that essentially in trapped ions, you are given the qubit by nature. You essentially have some species, some element. Usually for us, it's one of these atomic species such as calcium, ytterbium, or something where if we strip off one electron and we charge it, then the level structure becomes easily manipulable by lasers. And this is how we conduct and encode sort of the quantum computations, quantum operations. And each of these elements is identical to every other element. So there's no issue of reproducibility. So for example, in the superconducting machines, the qubits are essentially assembled, right? They're built from circuitry, and it's not always easy to have a machine that you can serialize and produce, because there's always going to be small deviations. And I think it takes a lot of effort to get the computer to a running, let's say, state where you've characterized everything perfectly, you've cooled this machine down to almost near absolute zero to run it, you wired everything, and there's a lot of complexity and beautiful engineering that is going into this, but it's not obvious that it's going to be easy to take what we can do with 100 and 500 qubits where people are doing things by hand and be able to build an industrial size computer that will have 10,000 qubits. Whereas with the app, yeah.
Sorry for interrupting, but as a quick follow-up to that question, Is it the case that for trapped ion quantum computers you have less calibration efforts as well compared to, for example, superconducting? So my understanding is as a consequence of what you just mentioned, the particularities around the circuitry of a superconducting quantum computer, you have large demands on calibration, for example, when you try to put together these large assemblies of... Yeah. Is that smaller for trapped ions?
I would say it's transferred to different parts. You're not necessarily calibrating the qubit, you're calibrating the devices used to control them. So in that case, for us, it's the laser fields or the microwave fields, for example, and the environment in which that qubit resides. So for example, our ions tend to be sensitive, for example, to magnetic fields. So what we're looking at is, isolating the field, making sure it's very stable, making sure there's no magnetic field gradients that can shift these frequencies. But essentially, the qubits themselves are identical, right? So if you can build a system that you can calibrate well for 50 qubits and you can manipulate them and you have a clear architecture, clear path to go forward, then it doesn't necessarily become so much more complex, right? So you have this beautiful reproducibility and the system is perfectly well understood on a physics level. And then it becomes more a question of simply engineering the control fields. And of course that's a difficult issue and it's something we're going to have to cope with when we also try to go to larger amounts. But I think that's where the key distinction lies, that if we build one ion trap computer and we know very well what goes on into building it, building a second one is not going to be hard. And I think that's going to be very relevant for us, I think. So you can imagine, for example, modularizing computers, connecting them in the future, for example, be it through like optical interconnects where you send information across optical fibers. As long as you can build one reliable machine with n qubits, you can then build many machines like that, because the underlying technology and the atoms you put in are always going to be the same. Now, of course, you're right, calibrations are inevitable, they're a fact of life, and there will always be overheads spent on this. But, I guess my hunch or my opinion is that it's going to be less of an issue for trapped ions.
Okay.
Yeah, and I guess the other way to look at it, the other way to compare is that, I guess with trapped ions, what we really hope to do is this sort of architecture where we can move into 2 dimensions. So we want to take, so typically what people have worked on, maybe taking a step back, is that we've had strings of ions. We've put these ions in a long chain where really they're separated like this by a few microns. And we take lasers and we can shine them at each individual ion to perform the sort of quantum operations. But of course we can't just build these chains super long, because after some point you simply cannot fit enough ions in, let's say, the confining volume of the electromagnetic field that we used to trap. For some technical reasons, but essentially this won't scale. So we know we have to go to 2 dimensions and turn your chain into a grid. And then what I think is that the pathway to do this is somewhat clear, and it's been known for over 2 decades now. And it's an engineering challenge. But we at ETH hope to have a kind of a breakthrough that should simplify one of the big engineering bottlenecks, and that's in the form of heat dissipation. And this is something that's always troublesome for many systems, but it's a very technical and uninteresting thing and doesn't really often get put in the media. But one of the problems, of course, is when you start going to more and more systems, you're trying to cram things on a small chip. And just as with classical processors, the more transistors you put on your Pentium chip or your AMD chip, it just heats up. And getting this heat out is very difficult. And so going to a large architecture, even ion traps, is going to be very difficult because you're having to feed in lots of electric fields that often oscillate at a radio frequency to actually trap the ions. And maybe what we want to do, and this is now kind of alluding to the research I do, is we want to dispense with this trapping of these radio frequency fields and use a magnetic field instead to trap the ions in 2 dimensions. And using this, we hope to be able to build these larger grids in a much more favorable environment with much less heat dissipation. And this, for example, is one of those things that I'm talking about. So there was this huge bottleneck of engineering, and suddenly this bottleneck might be gone. And now you can maybe go from 100 to 1,000 without a huge increase, in energy cost. And so I do think that there's definitely advantages here that, for example, the superconducting people will always face. They have to have these really strong fridges where they cool much lower. They go almost near to absolute zero. Whereas typically, if we say cryogenic and ion traps, we mean 4 to 5 Kelvin. So we're not as demanding on the cryosystems themselves, and so I hope we could, show that we can be more scalable in this sort of fashion. Yeah.
Mm-hmm. Do you have a conceptual explanation for why moving to magnetic fields might help with heat dissipation? I know, I mean, you could probably explain it, but it would be very technical. But I'm just wondering if there's a quick way to sort of get a grasp of why that would help.
I think conceptually it's it's a bit hard maybe stepping back to with the nature of actually how the ion trap works. But essentially, there is a fundamental theorem that says that you cannot trap a charged particle just with static electric field. So if you imagine it as if, I create some sort of well, right? And you imagine you want to put a ball at the bottom of the well, and that means you need to be able to push on it from this side, but you have to imagine it also in 3D, so it's harder to visualize, but essentially what electromagnetism says is there's always one direction on which the particle will try to escape, right? So instead of having, let's say, a well, you can imagine that your particle sits on top of a saddle, right? In one dimension, there's a restoring force, but in the other one, there's a force that's sort of pushing it down. But now if you rotate this saddle really fast, you can imagine that the particle, as it tries to go off, roll down the hill, the surface underneath it rotates, and now the particle will see a restoring force back to the center. And so, so physically, this is a kind of conceptual explanation. The faster you rotate, and if you rotate at the right frequency and have the right saddle potential, you can confine a particle like this. And the analogy here is that if you translate this to electric fields, you have to have an oscillating electric field, and then you can overcome, let's say, this limitation that the ions cannot be trapped with, static electric fields. The problem is these oscillating fields is that they have to oscillate usually at tens to hundreds of megahertz, and the amplitudes of these fields are usually also, for example, in the tens to hundreds of volts. And if you do the maths and look at how much power you're essentially delivering to a small chip, right? So you have some chip where you trap your ions, and this is usually on the order of, the whole thing has maybe a footprint of a few millimeters, and the individual electrodes on which you apply these electric fields, they maybe have sizes of, 50 to 100 or so microns. And there's very small gaps in between these electrodes, maybe again a few microns. And so there's also a big capacitance between them. And so what ends up happening, you put a lot of power, and this power also dissipates in this system, and it heats the chip up. And this is very undesirable, right? Because if you start adding more and more RF lines, as you start moving, from one dimension to two, and you start building a grid of RF lines, then you will keep adding more and more power. And this is going to be really disruptive to the system, to its stability, and to, in general, the ability to even operate and maybe not destroy the chip itself if you go from, 10 to 100 or 1,000 of these lines. Mm-hmm. And so by replacing the confinement of the radio frequency fields with just the static magnetic field, this problem is completely gone. So this is known as a penning trap, whereby you confine in one dimension with a static electric field and in the other two dimensions with a magnetic field. And so it's a different way to trap ions, but yeah, essentially that's what we want to do. And what we've shown for the first time ever is that we combine this penning trap approach with a small chip trap. Because these penning traps have existed in the past, they're nothing new, they've been around for many decades, but they've usually been very macroscopic. And people haven't really thought of using them for quantum computing. They've been used, in precision measurements. They're employed, for example, in CERN. They're used as mass spectrometers, but never really as these small chip traps that can maybe form the future of a scalable quantum computer.
Mm-hmm. The other question I would have, and this alludes back to what we were discussing before, is if you put these in a grid, so let's say you want to scale it up more effectively and put your ions in a grid, how would that actually result, or what would be the consequences be in terms of interference between the ions when you try to measure it? So my understanding for this is when you try to measure it, you send essentially a laser that resonates with the ion, and then the emitting photon allows you to measure which of the states this particle is in.
Yes.
And sometimes my understanding is this photon that is then sent can interfere with the other ions as well.
Exactly. That's a very good point. And this is exactly what this architecture is sort of designed to do, right? So when you have the ions close to each other, like I mentioned the chain before, let's say there's ion 1 here and ion 2 is 5 microns here. You shine your laser at this guy, and now it re-emits these photons, and if this guy's nearby, then there's a small chance, but not negligible, they get hit by a photon. But now if I move this guy very far off, I take him, hundreds or 500 microns away, then the probability of getting hit by that photon decreases drastically. So the way the architecture handles this is by shuttling the ions away from the ones that are being necessarily manipulated. And so I guess in the parlance, we can usually say that there's a memory region where no lasers are being shown. And usually this is somewhere, let's say, far away from the interaction region where there's a lot of lasering going on. So you can have this reconfigurability of your system where the ions can be moved away, or let's say mitigate this sort of issue by simply separation.
Mm-hmm. And then you physically move the ions with the help of an electromagnetic field. Exactly,
yeah. And so the big advantage for us is that because we can create really large and nicely homogeneous magnetic fields using, for example, magnet technology such as those used in MRIs, right? So we have superconducting magnets that can generate very nice, stable, and very homogeneous fields that over large areas. And then we simply change the static DC potentials on these electrodes to then move the ions from spot X to spot Y. And the thing is, we can do it completely in 3D. And this is the big step forward compared to the traditional ion trap approach, where the ions, you could imagine, were sort of being driven along street blocks. You always had intersections, and you were always basically in this line. And to go to 2D, you would simply build these intersections. We would call them junctions, and you would shuttle these ions around like this. And of course, you can imagine that it's less efficient to get ion 1 to here if you have to go through a bunch of junctions than simply moving them through free space. And so hopefully this is one of the big advantages that we want to push and sell architecture by saying that it's going to be very efficient at reconfiguring these 2D crystals for the need of the computation.
Mm-hmm. How far along is that technology for physically moving the ions? So I saw a talk, I don't recall exactly when it was from, but my understanding was there's still a lot of questions, like how to do this practically, even in 1 dimension, or 2 dimensions rather, like if you want to move them and then sort of shuffle them around so that you can pass other
I would say
through. Yeah.
The technology's made quite a lot of progress recently. So in some sense, it wasn't that difficult. It was just really a question of engineering. Conceptually, it was pretty well understood what needs to be done. And it was, as soon as people threw a lot of money and expertise at it, it got better very quickly. So I'll give you one example. Honeywell, which spun off their quantum division, I think they're called Quantinuum now, they like to use this architecture. And their approach is still using radio frequency fields for trapping, but they do exactly this. They can shuttle around the ions in 1 dimension, and they can, for example, rotate them, split these strings, join them, etc. And they've got really good success with this. They've demonstrated some really nice error correction results using these systems. And they've now also demonstrated very recently that they can go around these corners very nicely without paying a big penalty on disturbing the motional states of these ions, which is very important when you look at sort of long-term error rates of your quantum algorithm. So they've made a lot of progress. They've even shown that if you have 2 different species, right, which they use in their system, 2 different elements, and you move them together across the junction, you can still do this effectively. So this was a very recent result. I think it was shown last year for the first time. So exactly this, and I think this really relies on detailed knowledge of people building these chips, knowing how to apply the potentials, knowing how to calibrate them, and doing lots of optimization. And then you can make really good progress. So I would say that on this level, the progress has been really nice. And then what we're doing at ETH is actually made a lot simpler because we don't have these junctions at all. So for us, it's almost trivial. We simply change the DC field and we just slowly change the DC voltage and we just drag the ion along. So, I mean, I'm not going to make any bombastic claims. We're kind of working with 1 ion right now. So we don't have a grid, but we can show this 1 ion, we can really move anywhere. And that's really nice. And there, I don't even see how it's going to get more difficult. The only difficulty is going to be, of course, when you have lots of them, it's going to be a lot more complex, the sequences you apply. But the physics won't change, right? So I think we've shown that it's really good. and it has a really nice potential. So that this is kind of an innovation, I believe, that we'll be hoping to publish very soon some results on this.
Mm-hmm. Interesting. So besides the fact that you would need to shuffle your ions in a slightly different way if you go to 3D, are there any other issues or like that arise either from an engineering point of view or from a conceptual point of view in moving to that kind of grid structure, besides what we just talked about with sort of, well, avoiding the interference between the ions?
I mean, one thing you can imagine is once you start going to a large grid, right? Typically what we do now is you have, like, let's say this is the surface of your chip and you have your chain like this. Then your lasers can come nicely along the surface of the chip and pick out each ion. But now if you imagine there's a grid of ions, well, if you try to hit this guy and there's another ion sitting behind him, well, that's no good. The laser will hit both of them, right? So really maybe the future of the approach to address ions with lasers is actually to have the beams come out of the surface. And this will call for integrated optics. And that means, for example, you send light through the chip itself by having integrated waveguides in the chip. And then you have, for example, some grating outcoupler that's sitting just underneath one particular ion site and sends the light out and will just hit this one particular ion. So of course this greatly increases the complexity. It's another layer of engineering, but it's something that's also seen lots of progress in the recent years. So there have been some really good results of integrating optics, waveguides, etc. in these trap chips. And this would be a way, for example, to then deliver the light scalably to different zones in a 2D array without worrying, for example, how will you shoot the beams in, from the outside. So I think this is a potential avenue that could help us out a lot.
If we're thinking about additional problems with coming back to scaling again of these quantum computers, are there any other ones you would like to raise? I'm thinking like when it comes to, for example, the logical gates, specifically when we're talking about, for example, entangling, how you would handle that, how you currently handle it, maybe would be interesting from a trapped ion perspective, but then also going forward, how you would be able to do that in a very large system.
So I would say right now, trapped ions have the best entangling fidelities out of all the systems. So I think we hold the records for the highest fidelities where we can get to 4 nines. So there have been some academic results where you can get to 99.99% fidelity. But of course, these are usually done in systems that aren't designed to be scalable. They're usually small scale demonstrations. Once you start averaging over a whole qubit register and more like say these commercial machines, then you start looking at more like 99% fidelities, right? Because it just becomes harder and harder to ensure that entangling any one ion with any other ion is done to the same level of fidelity. And this is maybe the price you pay by having to shuttle them all around, which actually takes time. That's one of the downsides of this approach, is that moving the ions around is kind of slow. When you think of the time scale of how fast information moves on, like, let's say your CPU chip in your actual classical computer, then this thing is running at gigahertz, whereas moving the ions around is actually pretty slow. It takes microseconds to do this, or sometimes even much longer than that. And so that means your information has to be very robust and survive, and so as to survive the time scales given to you by decoherence, all these other processes. So the gates, or let's say the fidelity of the information, has to live for a very long time. So that's one challenge, and then that comes in with isolating your system against all your external disturbances, as I mentioned, magnetic fields, etc. And then the actual gates themselves, of course, have to be done very well over many spots, and there'll be a level of parallelism necessary to achieve, let's say, the computational efficiency, right? So you can't just have 100 qubits but only ever be entangling 2 out of those 100 at one particular time. Then it'll be really slow to build the algorithm. So there's a level of parallelism that has to go in, so you can entangle in parallel in different spots. And you have to ensure that all these different gates are all run at these high fidelities. So there's a huge challenge of taking this fidelity that we can achieve in our test system in the lab, like at some university, and making this applicable over the whole range of the chip in all the different zones with all the different ions. And that's definitely a challenge. But on the gate technology itself, I think there's a lot of approaches that say the fundamental reason that you can't, or I say there's no fundamental reason why you can't reach even higher fidelities. Typically, it's always technical noise that's limiting you in these cases, right? So as laser technologies get better, as microwave, let's say the tricks we use to employ microwave gates get better, the fidelities might also get better. I mean, it's a bit of a slow crawl up in these fidelities, and every next, let's say, digit of precision comes at a big cost. I think it's doable, and it's going there slowly, but I don't think that it's necessary to make the fidelities that much better if we can scale up the number of qubits well, right? And this is where the error correction will come in, right? So there's these thresholds that say you need to have at least this much fidelity for a particular error correcting code to work. But once you're over this threshold, let's say by some safe margin, then it's a question of really scaling up your system. And now here, maybe coming back to your question, but moving away from the fidelity, what are some other challenges I foresee? So one of the big challenges is, of course, controlling this many electrodes, right? And this is very complex, right? If you imagine that each electrode needs to have some external control line that sets a particular voltage for that electrode. To build this 2D grid, we're going to have many, many electrodes. And just kind of back of the envelope, if you assume one ion, it needs at least 5 or 6 electrodes to be able to manipulate it, let's say 6. Then for large arrays, you're going to need many thousands of electrodes. And each one of these will require its own input voltage. And again, this will be extremely demanding, and we'll need some level of parallelism here that will allow you to actually exploit, let's say, some symmetries of the chip, such that you're not really in real time editing 1,000 different voltages, but maybe you're somehow recycling signals along the chip, such that you can minimize this overhead of trying to feed all these signals in. So again, it's not trivial, but it is more an engineering problem than a physics problem, I would say. But the physics really, in terms of the gates, doesn't prohibit us from reaching really good fidelities. Typically, it's a question of making your control better.
Mm-hmm. And for the current large systems that you have for trapped ions, how many qubits in that system have we been able to reach, roughly speaking? Are we already running into those problems, is what I'm trying to get at, with the electrons growing out of hand, or is that something you foresee as a potential future problem, but not really a problem?
Yeah, I think this is a bit of a future problem that we're going to be seeing very soon. But I believe, for example, the commercial system from IonQ that they've launched is something like 30 qubits. What Quantinuum have, they're also sort of in this 20 qubit ballpark. So let's say they're not even at the level of Google or IBM yet, but they're achieving they get more bang for the buck for these qubits, right? Because one thing they have that the other systems don't have is all-to-all connectivity. That means that if I want to entangle this ion with this ion, it's a question of reshuffling them to be in this interaction zone and then entangle them there. Whereas if you want to do this in an IBM system and you have this sort of grid of connectivity, the superconducting qubits cannot move. So you need to really entangle something here with something there. There's a lot of steps in between. I mean, I picked, of course, the worst case scenario, but this connectivity does actually contribute significantly when you start looking at running actual algorithms, right? And so this is something I think we can exploit as an architecture compared to the superconducting approaches.
Mm-hmm. For the ones, so for the big ones that you just mentioned, the big ion trap quantum computing systems, do they currently rely on error correcting codes as well in some fashion, or are they?
So I guess rely is maybe not the right way to put it, because in some sense no one's really doing useful quantum computation, right? There's no, let's say, commercial advantage to doing this. So anyone who's working on error correction is doing it because they know future systems will rely on it. So I would say now is the research phase when people want to demonstrate, look, we can do error correction, we can do it with, we can show all the building blocks that are necessary to build an error correcting quantum computer. I think that's the stage we're at. And for example, Quantinuum have been publishing results where they have done this. So I wouldn't say rely, because let's say if a customer wants to run something on a cloud system, they can do whatever they want. They can run whatever algorithm, but they're not going to be running it error corrected. There's just not enough qubits for that at the moment, of course. But these systems can do elementary error correction if they're programmed to do it.
And is there a particular problem with scaling that error correction up to a larger number of qubits?
I think the problem of scaling error correction is simply the problem of getting more physical qubits to represent the logical qubit. So I guess the principle is that you create one logical qubit out of many constituent physical qubits, which somehow encode this sort of quantum redundancy that you need. And yeah, the more, if you want to protect yourself against all the possible errors, and it's just, the overheads are huge essentially. So to really build a fully error-corrected quantum computer, you need a lot of physical qubits in order to turn them into logical qubits. And there's a vast array of codes that I'm no expert in this field, so I don't want to throw out any numbers, but yeah, usually you need quite a few physical qubits to run realistic, useful algorithms that would, for example, be, I don't know, something like factoring large prime numbers, the Shor's algorithm. You would probably need, I don't know, hundreds of thousands of qubits physically to be able to do it with enough logical qubits to make it interesting.
Mm-hmm. Okay. Mm-hmm. Besides the points that we raised, are there any other ones that you think are going to be potential difficulties when it comes to scaling up the technology in general?
I mean, maybe instead of talking about difficulties, I'm going to throw a bit of a curveball here and just say what's some potential unexplored pathways to winning a bit with the systems we have. And this comes back to some research I did at the University of Innsbruck, which was in the field of encoding information in Qudits. So the difference between qubits and Qudits is that a bit implies there's two states that you're encoding information in between, and of course because it's quantum you can get all superposition between these two states. But a Qudit leverages the fact that, for example, an atom has many different energy levels. So your single atom can actually encode a lot more information that we usually use it for. So you can imagine increasing the density of information per chip can be achieved by simply encoding in Qudits rather than qubits. And now the research that we've done was essentially take a very common ion that's used in many different quantum computing groups around the world and simply use more of its energy levels to encode information. And so instead of a bit, we encoded 3, 4, and 5 level Qudits into this system. And we also showed that we can entangle two Qudits with each other with very high fidelities. And here, I think a lot of the fear was that from other people, why do you do Qudits? It's just only going to be harder. Qubits are hard enough as it is. Why would you bother going to these systems? And I guess what we showed is that we came up with a completely new gate entangling mechanism that actually doesn't scale the complexity of calibration at all with the number of Qudits. So if you calibrate the system on a qubit, doing that same exact gate on a Qtrit or Q-quart, which is the term for a 3-level or 4-level system, is very simple. You just change the power of your laser by a known amount, and boom, you can entangle these. Okay, the fidelities weren't as good, but we were still in the high 90s range for these systems. So if we were getting 99.6% for the qubit, for the Qtrit we still got 99, for the Q-quart maybe 97. So yes, it drops off a bit, but maybe with enough work from theorists and people who use these results, we can maybe design more efficient algorithms that harness this additional information to, let's say, to our benefit. And of course, these fidelities I quote, again, they're not fundamental limitations. They're simply coming from the fact that it's harder to control these many levels because of calibrations and control in the laser systems. But there's nothing fundamentally saying that these gates should be lower fidelity. In simulation on your computer, the fidelities can be awesome, right? So it's again a question of, if we put a lot of hard work in, maybe we can help ourselves a lot, because it's going to be hard, as you said, engineering problems, electrodes, all these things, there's probably going to be a limit beyond which it's going to be hard without, for example, modularizing the computers. But then if we can increase the density of information in this module by using more levels, we can again stand to gain a lot. So this is something I also find interesting, and it's quite a young field. There's not so much research in this, in Qudits, but I think we've shown a very important, let's say, milestone in this approach that hopefully encourages others to keep looking in this direction.
Mm-hmm. I think one interesting follow-up question on Qudits is regarding the energy levels of the particles that you're using for encoding the information. So I would assume that that becomes a larger consideration when you talk about qubits and when you generally leverage more of the energy states of your ions. Do you have sort of clear-cut materials that are very good for encoding multiple levels of information, or is that something that's somehow problematic right now? I'm thinking particularly if there's like a need for investigating other materials, maybe even like molecules, if that's even possible for these kinds of applications, or whether you already have sort of everything you need in terms of just using, I don't know, calcium atoms, I think is the most common for these applications.
Exactly. So I think that's a very good question, and so of course there are limitations to what we can encode in because there's not infinite many levels. So in terms of what you can achieve realistically in a particular atom is simply given by the atomic physics, which tells you what are the energy levels that are accessible with the lasers you typically use. And let's say just sticking with the example of calcium, we would probably be able to encode at most, I'd say 7 levels of information for this particular atom. Now, if you switch to a different atom, for example, one that has hyperfine structure, that means there's more available energy levels per, like they can maybe go to tens of energy levels. But it's not going to jump to 100, I think, at any point. So I think that the range in which you're going to be making any gains is probably in the single digit to 10 digit to tens of levels. But I think it's going to also get very hard to manipulate such large manifolds of energy levels. So and it's going to exactly depend on which atom you choose. The question with molecules, of course, is yes, people are looking into molecules. There are more and more experiments with molecules in trapped ion systems. I would say, again, that's another huge jump in complexity. And I hesitate to even say when this might happen, at what point people will really start doing computations with them. But I would say never, and the better we get at controlling these systems, then yes, of course, you can find even more interesting encodings with more degrees of freedom that molecules can offer you, for sure.
Understood. We should be bringing this to a close because we're running up on time, but just before we do that, I would like to ask if there are any sort of points of advice that you would give to the academic field in general, like where you think more research needs to be directed to enable the scaling of these kinds of systems?
Yeah, I mean, I would say that what I would maybe advise the field is to, I don't know, sometimes give more prominence to these sort of technical issues. I think that maybe it's not what is glossy and it's not what you end up putting into your Nature publication, but in general, I would love if people communicated more at conferences about like these niggly little issues that are exactly the type that we talk about today: calibration, scaling, the engineering aspects of things, because I feel like a lot of times this gets stuck behind the scenes, and it's what the PhD students talk about, it's what the tech research people talk about, and it often is what's missing from the more higher level discussion. And I would love to have maybe more open discussions about this. And likewise, for example, I would be happy to also learn more about what the challenges are with the other architecture, with superconducting qubits or with neutral atoms. But of course, everybody wants to first say their best, newest, freshest, cool result, rather than start talking immediately about their issues and difficulties. But I think by talking about the difficulties, and being upfront about them, is when you really stimulate people to think hard about them, take a step back and think, have we been, just rushing to pick all the low-hanging fruit of this architecture, and does it really have the potential to scale, and will we hit hard bottlenecks when we go past a certain number of qubits? So, I mean, maybe this is what I would say in general to almost all the sort of quantum computing fields.
Perfect. So I think there we can bring it to a close. Thanks a lot, Pavel, for taking the time to join today.
Yeah, thanks very much. It was very fun